In this video, I will talk about pneumatic flow rates. Pneumatic systems usually use air, and air is a compressible fluid. So let's talk about compressible flow. I have here a pipe that reduces down through a neck and then expands back out to the same size pipe. The pressure upstream of the neck is given as P1, and the pressure downstream of the neck is given as P2. Let's say that P1 was 100 psi A, and pressure P2 was also 100 psi A. Well, we would get no flow through the neck, because flow is caused by pressure differences, and if there's no pressure difference, we get no flow. What if the pressure P2 downstream of the neck was lowered to 90 psi A? Well, then air would begin to flow from the pipe through the neck and back out into the pipe. And because the pressure difference is only 10 psi, let's call that slow flow. And the flow rate is equal to the velocity times the area, and if the velocity is pretty slow, then we'd get a pretty small flow rate, simply due to the fact that we have a very low pressure drop across that neck. If pressure P2 was lowered to 75 psi A, now we have a larger pressure drop across the neck. That would result in the air flowing faster through the neck. Let's call that medium speed. And because the flow rate is the velocity times the area, and we have a medium velocity, then we would get a medium flow rate through that neck. If P2 was lowered again to 60 psi A, a larger pressure drop across that neck would result in the air flowing faster through the neck. And of course, because the flow rate is the velocity times the area, if the velocity is fast, then we'd get a high flow rate through that neck. If I continued to lower the pressure P2 to 53 psi, we would find that the air traveling through the neck would reach the speed of sound. And physics tells us that compressible fluids going through a reduced opening can never go faster than the speed of sound. And since flow rate is the velocity times the area, and the velocity now is the maximum that the velocity could ever be, we would now see a maximum flow rate through that neck. We call this choked flow, when the speed of the air going through the neck reaches the speed of sound. If I were to lower pressure P2 any lower, I would get no additional flow rate through this neck, because the flow is choked. And we find as a rule of thumb that the maximum flow rate of air through a neck occurs when pressure P2 is 53% of P1, or the P2 over P1 ratio is 0.53. So if I were to continue to lower pressure P2, let's say to 14.7 psia, or in other words, the pipe on the right-hand side was just venting to atmosphere, the air traveling through the neck would not go any faster than it did when pressure P2 was 53 psi, because physics tells us that air going through a reducer cannot go faster than the speed of sound. So there would be no increase in flow rate. Lowering pressure P2 lower than 53% of the upstream pressure would not increase flow rate at all, because the flow had been choked. So let's talk about how to calculate flow rates through valves. In hydraulics, it was very straightforward. Hydraulic fluids are treated as incompressible, and the equation that we used for that was Q equals C sub V times the square root of delta P over the specific gravity. Q being the flow rate through the valve in gallons per minute, C sub V is the capacity coefficient in gallons per minute per square root of psi, and the delta P was the pressure drop across the valve in psi, and the specific gravity. Determining flow rates through pneumatic valves is a little more complicated. The equation is similar, but instead Q is the flow through the valve in SCFM, standardized cubic feet per minute. That means that we've taken the flow rate through the valve and standardized that flow rate to atmospheric conditions. You'll also notice that it has a constant in front of the C sub V, and the textbook actually uses a constant of 22.7, but the pneumatic specialist exam will use a slightly different number than the text, this 22.5. The C sub V is the capacity coefficient. And you'll also notice under the square root that we have P1 minus P2. That's the delta P, very similar to the hydraulics equation. But we also have P2 here. And whenever we have pressures that are multiplied, we have to use absolute numbers. So these pressures here, because it was a difference in pressure, we could use gauge pressures. But here we have to use an absolute pressure. and this is the temperature, and that has to be in absolute numbers as well, degrees Rankine. And usually we will assume that the pneumatic system is at room temperature, or 70 degrees Fahrenheit. Now this equation is a little more complex, but it even becomes more complex when we realize that this equation is only valid when the flow is not choked, or when the pressure 2 to pressure 1 ratio is greater than 53%. If the flow is choked, or P2 over P1 is less than 53%, then the flow rate must be calculated using the choked pressure. So let's look at a specific example. We're going to determine the flow rate in SCFM through a directional control valve that's connected to an 80 psi source with downstream pressure P2 equal to 60 psi. So here's our scenario. 80 psi source, a directional control valve whose CV is 3, and this is connected to a pneumatic circuit such that P2 is 60 psi. Well, the first thing we need to do to determine the flow rate through that valve is first check to see if the flow is choked or not. And we do that by taking the ratio of P2 to P1. And because that's a ratio, we have to use pressures in absolute numbers. So notice we've added the 14.7. And that will result in a 79% ratio. That's clearly greater than 53%. So the flow is not choked, so we can go ahead and use this equation. And notice that we had to use an absolute pressure here for P2 and an absolute temperature here for T1, and we're just using room temperature. And we calculate that to be 113.3 standardized cubic feet per minute through that valve. What if in this example the pressure was decreased to 20 psi instead of 60 psi? Well, we'd go through the same steps. First we have to check to see if the flow is choked. The P2 over P1 ratio again uses absolute pressures and would be 37%. That is less than 53%. So that tells us that the flow is choked, that the air traveling through the valve has reached the speed of sound. So we've got to figure out which pressure P2 would have caused this system to be choked, or equal to 53%. And we find that this would have been choked if the downstream pressure P2 was 35.5 psi. So now as we use this equation, we use the 35.5 psi because we know the flow rate will never get greater than the flow rate at that pressure. And we find that that's 138.6 standardized cubic feet per minute.